In the physical world, variables rarely move in isolation. When one metric shifts, it pulls and pushes on others, operating as an interconnected system. This split screen compares our standard analytical approach with that reality. On the left, a single variable model captures a simple probability curve. On the right, a bivariate model maps thousands of interacting data points across multiple dimensions. If you extract these variables and analyze them strictly one at a time, you completely ignore the underlying geometric structure dictating how they move together. To capture that structure, we will construct the complete mathematical framework for bivariate probability, moving step by step through joint distributions, then marginal distributions, and finally conditional distributions. Attempting to bypass this mathematical foundation and relying entirely on a single summary statistic, like standard correlation, creates an analytical blind spot that routinely compromises risk and portfolio calculations. We begin by introducing a discrete system of two interacting random variables, x and y. This grid represents their joint probability mass function, notated as p of x, y. Rather than looking at outcomes in isolation, this matrix calculates the exact probability of a specific x value and a specific y value occurring simultaneously. Because this defines a valid closed probability space, the sum of all simultaneous probabilities across the entire grid must resolve to exactly 1. Therefore, the joint PMF provides the strictly complete informational picture of the entire system. No interaction, overlap, or dependency between the variables is hidden from this matrix. From this full picture, we can derive the marginal distributions. These isolate the probability behavior of a single variable by entirely ignoring the other. The mathematical operation for this is marginalization. To isolate x, we sum the probabilities across all possible values of the unwanted variable, y, compressing the grid into a single row. We perform this same operation symmetrically to find the marginal distribution of y, summing across the columns to compress the data horizontally. This establishes a rigid asymmetry in joint probability. You can always collapse a joint distribution to find the marginals. But because that collapse permanently destroys the structure of how the variables interact, you can never mathematically reconstruct the joint behavior using the marginals alone. To observe that interaction directly, we fix one variable in place and measure the behavioral reaction of the other. This creates a conditional distribution. It is a literal geometric slice of the joint distribution taken at a specific fixed value, in this case where y equals 1. To make this isolated slice a mathematically valid probability distribution, we normalize the raw values by dividing them by the marginal probability of that fixed y value. The resulting fractions now correctly sum to 1. With these distribution mechanics established, we can mathematically define statistical independence. Two variables are independent if and only if their joint distribution factors exactly into the product of their individual marginals for every possible pair in the system. We can test this rule against our grid. We isolate coordinate 0, 0, which has a joint probability of 0.1. We then multiply its individual marginals. 0.3 times 0.4 yields 0.12. 0.1 does not equal 0.12. The factorization fails. A single mismatched data pair anywhere in the entire matrix is mathematically sufficient to disprove independence for the whole system. These variables are dependent. We can now apply these mechanics to a physical engineering problem, calculating the total risk of an industrial machine built from two dependent components. Component X has a known variance of 9. Component Y has a variance of 16. Because they are mechanically interlinked, they possess a correlation coefficient of 0.5. When adding dependent variables, their individual variances are not strictly additive. We have to account for their combined movement using this formula, which includes a critical scaling factor, covariance. Covariance is the unstandardized measure of their linear directional relationship. We calculate it by multiplying their correlation by the standard deviations of both components, yielding a covariance of 6. Inserting that back into the equation reveals a total system variance of 37. If we had falsely assumed the components were independent, we would have expected a variance of only 25. That extra covariance term dictates exactly how much systemic risk is compounding. This specific mechanism is the exact engine driving catastrophic aggregate risk failures. as well as the mathematical basis for portfolio diversification. This brings us to a common and fatal modeling assumption made by applied analysts: the belief that a covariance of 0 mathematically guarantees statistical independence. The rule only works in one direction. True mathematical independence will always result in a covariance of 0, but the inverse is entirely false. Consider a scenario with a variable, x, defined by a uniform distribution between -1 and +1. We define a second variable, y, exactly and deterministically as x squared. Because the uniform distribution is symmetric around 0, x's expected value is 0. The expected value of xy also integrates to 0. Subtracting these leaves a perfect covariance of exactly 0. But plotting this underlying data reveals a rigid, unmoving pattern. There is a stark contradiction between what we see and what the metric measured. Y is completely and deterministically driven by x. There is 0 randomness in how they interact, yet the standard covariance formula misses it completely. This exposes a massive analytical blind spot. Covariance and its standardized counterpart, correlation, exclusively measure linear association. Because the math is fundamentally only looking for straight lines, these metrics are completely oblivious to nonlinear structures. In exploratory data analysis, a correlation of 0 confirms there is no straight line to be drawn. It does not mean the variables are unrelated. Real-world physical constraints and complex economic phenomena frequently follow curved, nonlinear paths. These structural relationships will hide entirely from standard correlation matrices. To accurately quantify risk and avoid catastrophic modeling failures, summary statistics are never enough. You must rigorously interrogate the complete joint distribution.